sounded like an oddly cheerful version of the theme music of Papers, Please. Alright, hello everybody. Welcome back to the final episode of Human Resource Machine. Today we're going to finish the game by doing the speed challenge for sorting floor. Last time we did a couple of different solutions. One of them was to find the smallest element among all the remaining ones and then swapping it to the front. And that one was an algorithm called selection sort. And the other idea to improve the size of our program was to always swap the smallest. As soon as we see a smaller one, we swap it out to the front. And that's a variation of the algorithm called exchange sort. And like I mentioned, there are only like 100 ways to sort elements. So this time, in order to speed up our program, we're going to try yet another different algorithm called insertion sort. And the reason I want to do insertion sort is because with the previous techniques, we had to do this swapping, and each swap takes 6 instructions, and I think that is too much. And so I want to minimize the amount of swapping that we have to do, which insertion sort is pretty good at doing. So, starting at the bare bones program where it just copies all the inputs to the floor, this time I'm actually going to process one input at a time as soon as we read it out of the inbox. So take 75 for example, we're going to copy it over here, that's fine. But the next number, when we get 34, we're going to sort this among what we have on the floor immediately. So 75 is going to get bumped up to the next slot while 34 gets inserted into the slot where it should go in the sorted order. The next one, when we get 51, we're going to start at the end, and it's going to bump 75 over by another slot again, but then 51 is going to get inserted here because 34 is smaller and 34 doesn't need to move. And this way, we don't need to do any swapping at all. All we need to do is, if necessary, we'll bump the value up by one slot, and that doesn't need any swapping because the next slot didn't contain anything to begin with. So that's the idea here. Let me first copy just the first element because we know the first element always needs to go on the floor and there's no sorting involved. So let me do that immediately. Copy 2, which the address at 20 is going to be 0 anyway to start with. And then now there's the loop where we read each element in the inbox. If it's 0, I think we can just go down immediately, and this is where we're going to do output. If it's not 0, then don't copy it to 20 immediately. This is where we need to insert. And once we're done inserting, we do bump up 20 and jump back. Actually, should I bump up 20 immediately? Yeah, let's make the 20 the count of elements that we have so far. So this is the number of elements that we've put onto the floor so far, and at this point it's going to be 1. Every iteration of the loop we're going to bump this up. That's correct. Next up, what do we do in the insertion case? We want to start at the end, which means we have okay, let's put this at the end. Anyway, this is not the count. This is going to be the last, the index of the last element that we have on the floor. So at this point it's 0, and then every time we write a new one onto the floor, we're going to bump that up. Now, insertion. We start at the last element, so we're going to copy from last, and we're going to copy that to another index. This is the index where we are comparing and bumping. And now let's get the element at the address of our index and compare that against whatever we have in our inbox. So let's say this is the input, and let me make sure I write that. Here. Make sure I write that into the correct slot. Okay, we have saved a copy of our input. We set up this compare against our input. Now if, fine, let me do it the other way around. Copy from our input and then subtract the value that we're comparing against. This way we can do jump if negative, and if that's negative, it means the value that we already have on our floor is bigger, and so we want to bump that up by 1. That will look like copy from value that we're comparing against, and then we need to move it up by 1 slot. So let me reserve another cell on the floor for that. Which one is our index? Copy from last, copy to 21. Let me copy that to 23 as well. And I'm gonna bump up the value in 23 so that it points to the next element. And copy from 21 and copy that to the address in 23. So this way I'm bumping up the element that is bigger than our input. Once we do that, we need to go back to the place where would that be? Here, where we compare. But before that, I want to bump down both of our indexes. So by bumping down 21, we're going to next compare against the previous element that we've written onto the floor, and 23 is the element that we swapped into if it was bigger than our current input. If it's not negative, then we can skip this work. We don't need to bump anything. And in fact, we can just jump out of our loop because we have found the correct place to insert our element. Once we have found the correct place, the next step is just to write our input into the correct place. So I'm going to copy to this is not the correct index. I want to copy it to the one after the one that we compared against. This would be an empty slot. And then, I need a value to copy from our input. Input goes into that slot. Oh yeah, I forgot to check that we are done. So this one, jump if negative. So if 21 becomes negative, then we've finished checking our entire floor. And in this case, we can jump out of the loop as well. Yes, but I also need to include this because then otherwise 23 is not going to have the correct value. Alright, I hope that is correct. I'm probably going to forget something. You know what? Let's just run through it and see what it does. See if I'm missing anything. So I'm writing 75 to the floor first. Next I'm getting 34. And then I'm setting up my indexes so that the index I'm comparing against is 0 and the index that it will be swapped into is 1. That is correct. I'm comparing, this is negative, so it should now switch 75 over to here. I'm decrementing everything, going to the next iteration of my loop. See, I did forget something. Why? Hold on. Why did I not jump? Because... Wait a minute. Oh, okay. Yeah. Bump minus 23 first, then bump 21, and we're going to compare if the value in 21 is negative. Let's try that again. So everything should be good so far. 92 gets shifted over, and then we're going to subtract, and now this is going to be negative, so it should jump out of the loop, get our input, put that in slot 0. And now we're done with the second element. Let's get our third element. Reset the indexes. So now we're seeing if 1 needs to be shifted over to 2. Compare the element. This is negative, so it does get shifted over. Now we're testing if 0 should be shifted over to 1. So we're taking 47, compare it against 25. This is positive, and so we don't do anything. And then we're copying 47 to the correct element. Yes, this is very good. Okay, now 0. Yes, when it sees a 0, it goes to the output. Perfect. Okay, now we can output our stuff. Yes, I got a comment saying if I'm jumping if 0, then I know the value I have here is gonna be 0, and so I don't need to copy from 0 again. So thank you for that comment. I'm gonna copy that to just any index slot, and I'm going to do my output loop. Copy from that slot and send that to the outbox unless... Ooh, I need to know how many elements I have. That is interesting. You know what? I'm gonna do things a different way. So let me do copy from index of 21, and I'm gonna subtract my in value. This way I'm reversing the order of comparison, and I'm still going to keep it jump if negative. This way it's going to, instead of sorting in ascending order, it's going to be sorting in descending order. The smallest one is going to be at the end, and that's going to be pointed to by our last pointer. Let me run through that and make sure I have it right. Okay, yeah, so now this is sorted in descending order, and my last is 2, so by the time I get to the output, I'm going to use the last index as my starting index. I'm going to work my way back to 0, so that I don't have to recalculate indexes and look for where the end is. Let's do that. I'm going to copy from the index in last instead, send that to the outbox, bump down, last, jump back, this is my loop, and then the only terminating condition is if last has become 0, then I can stop now and go back to the next array. This way, as you can see, there is no swapping involved at all, and I'm hoping this will be much faster in speed. You can't jump if 0 with empty hands. Okay. Right. I forgot to copy from... Okay, if I'm gonna copy from, I'm gonna bump this down, and I'm gonna go jump if negative. Very nice. We smashed the speed challenge again, and the size challenge too. I'm so happy to see this. We found a very efficient algorithm to be used on this level. Before I end this, I just want to show you a little bit of code that I would actually write in my day-to-day work. So I'm going to implement the same sorting algorithm that we did for sorting floor. So in my code, I would start by declaring a function called sort, and it's going to take as input an array of integers, and I'll call that list. Now I'm going to skip all the input and output stuff and just focus on the sorting algorithm itself. So first we have a loop with I starting at 0 and incrementing every time until we run out of the list. So the way I would write that is for int I starting at 0, and I will continue the loop as long as list at index I is not 0, and I is going to get incremented or bumped up by 1 each time it goes through this loop. And so that compresses this, the jump if 0 and the bump plus 1. I don't need to worry about any jumps. I just declare this scope between the braces to be my loop. And then same thing for j. I want my j to start at I plus 1. I want to keep going until my list at index j hits 0, and j also gets incremented by 1 every time. Next, we do the comparison between I and j and swap the two if necessary. And the way I do that is I say if list at I is greater than list at j, and then I'm going to swap. So I'm going to create a temporary variable, put list at index I into that. I'm going to reassign list of I to be list of j, and then list of j is going to retake the temporary slot, just like what we did in our game here. This is going to be the code that I write at my work. Now, once I have this code, I run it through a program called a compiler, which will translate the code that I write into machine code, which the CPU can natively understand and execute. And the machine code looks like this. Now you can see that the machine code is a lot more similar to what we have in our program, where you have individual instructions like move, test, jump, and add. And you can kind of see similarities between the actual machine code generated for the CPU for your regular desktop computer and the instructions that we have in our game. Here, for example, a move is basically a copy from or copy to instruction, and is copying from some pointer to an address in memory into a register. This is basically doing our copy from index I right here. And similarly, you have another move instruction that copies a different pointer to another register, and this is our copy from index j here. When it tests ECX against ECX, this is essentially testing if the value is 0, and if it is 0, then it jumps to L1, which is the end of our program. That's equivalent to the jump if 0 instruction that we have here, which goes all the way to the end of our sorting loop. And around here, it is comparing ECX against EDX. Those are the two values we've loaded earlier, and it's doing a jump if less than or equal instruction. This is comparing list I against list j, which is the equivalent of our subtract and jump if negative. After that, if it is negative, then it goes through here and it stores the values back into memory, but in reverse order. That is the equivalent of our copy to and copy from instructions here to swap the two. So as you can see, the game really takes you deep into the weeds of computer architecture and CPU instructions, and essentially makes you write a version of assembly language that the game has invented for itself. Whereas in my day-to-day job, I do not work with assembly at all. Instead, I work with higher level languages like C++ that I have here. In my work, I'll mainly worry about the data structures and algorithms that I use to make sure those are efficient, but I practically never get into the assembly level to optimize individual instructions or how many steps that the CPU is going to take. The compiler is actually very good at optimizing those things for me. Just to show you how good the compiler is at optimizing things, I'm going to re-implement the solution we had for the tetracountapplier level. So I'm going to start by declaring a function which returns an integer, and it's going to take as input another integer. Now the first step in our program is to take the input and put it into slot 0. So I'm going to declare a variable, and that's going to hold our input. The next step is to take slot 0, add it to another copy of slot 0 and put that into slot 1. So this is how I'm going to do that in C++. Takes slot 0, add another copy, and puts the result into slot 1. Next up, it takes slot 1, adds slot 1 and slot 0, and puts the result into slot 2. So that's going to be v2 equals slot 1 plus slot 1 plus slot 0. After that, we take 2, add a copy of slot 2, and put that back into slot 2. So that's going to be 2 equals 2 plus 2. We do that one more time. And finally, you take the result in slot 2, add another copy of itself, and put that in the outbox. The way we output is return, and I'm going to do v2 plus another copy of v2. And that is our multiplication function. Let's see what the compiler does with this. Yeah, the compiler knows exactly what we're trying to do, and it's able to find the most efficient way to implement exactly that on the CPU. So it's able to reduce our entire program with 6 lines of code and lots of additions into just 2 CPU instructions. Better yet, let's say I'm trying to use the function to multiply by 40 for real. Let me have another function called main, and I'm just going to call my tetracomultiplier function, and I'm going to multiply, let's say, 5 by 40. Now the compiler knows exactly what I'm trying to do. It knows this is a constant, and this function is going to multiply that constant by 40, and so it just immediately puts 200 into my program without even doing any calculation. So yeah, at work, when I'm trying to write a program, my concern is to make the program more readable for people, as opposed to being more efficient for the computer. Because I know, even if I write my program in a slightly inefficient way, the compiler is able to optimize what I write and make it efficient anyway. That's it, we have reached the end program. Congratulations.
Congratulations, you've really become an invaluable instruction follower.
Yes, don't worry, your job is safe. We've replaced you with this electric box.
It's called a computer. It iterates through a list of simple instructions, called a program.
It has a small amount of memory to store data while processing, like tiles on the floor,
It has inputs.
and outputs.
Its simple instructions can be used together in infinite combinations to compute just about anything you can imagine.
A truly efficient worker that never sleeps.
It's going to change everything.
Please take your things and enjoy whatever it is you people do out there. Congratulations.
Alright, and that is the end of the game. And now that I've finished the game, I'll just give a bit of my thoughts on it. Overall, I feel this is a pretty good teaching tool to get someone started on programming, or at least understanding how computers work at a very basic level. If you want to do good with all the levels and all the challenges, then you really need to change your frame of mind to really think like a computer. And that's a very important step for learning programming. It doesn't matter what language you'll eventually be programming in. So even for myself, I'm already pretty familiar with all this, but it was still a good exercise for me to do all this because it forces me to work with some new quirks and new limitations that came with the game's instruction set and CPU architecture. Another thing that I feel this game did really well is allowing you to go back and rework previous solutions. In fact, it kind of forces this on you by having size and speed challenges, where often it's not possible to meet both challenges at the same time. So that requires having multiple solutions. Also, if a solution fails or needs to be improved, then having the ability to debug it step by step, make changes, and try again, that is all very much like what I do in my real job. Now I'll talk about a couple of negatives too. The first thing that really annoyed me was that undo button. Most of the time, if your program is longer than one page, then you can't see what has been undone. The undo button stays at the bottom, and to click it, you have to scroll down to the bottom, but then that hides the top part of the program, so when you click undo, something changes on top, but you can't see what just changed. It's really terrible, and I just have to rant about this. Another thing is, while it does really good at teaching and simulating the programming aspect, it's honestly not much of a game, in that there's not much entertainment value. Pretty much all the levels are like your regular homework programs. They're just typical standard exercises that you'd expect to do when you learn programming for real. I feel like they could have made them more entertaining by coming up with some more interesting scenarios maybe, instead of literally giving you a CPU, some memory, and have you multiply numbers or sort elements. I mean, yeah, there are some short cartoon cutscenes mixed in there, but there's not much going on, and they have nothing to do with the gameplay at all. The story is very minimal and doesn't explain anything. So like 95% of this game is a pure programming course, and only 5% of it is actual game. Whether you'll enjoy playing through this will depend on whether you enjoy learning programming, which can definitely be the case, and in my case, I did enjoy this. So that is my final thoughts on the game. And to end this series, I have a tradition where after playing through every game, I'm going to read the entire credits out loud. Luckily, this one isn't very long, so... Human Resource Machine, created by Alan Blomquist, Kyle Gabler, Kyle Gray, starring Alice, Betty, and Carol. Bossman, Boss Lady. Translators, Ji-Hoon Bak, Victor Balog, Julian Blacktecki, Max Bruckner, Martin Blomers, Thomas Chapeau, Doruk Setin, Michel Colombo, Mathieu Cole, Gabriel Farina, Jean-Baptiste Naraka Daval, Karsten Gabriel, Luis Enrique Fonseca, Jean-Michael Gunderson, Bennett Gehring, Jana Halfway Lanza Jifeng, 1823 Studio, Alex Hernandez Puertas, Andreas Jesperson, Patrick Illenhalf, Maxim Love Irohinier Koshif, Cecilia Kelman, Joachim Holm Larsen, Igor Kuchera, Bello Bodor Martin, Jones Martins, Hithrock Mehagoto, Miroslav Mazel, My God Studio, Michael Mirage, Stefan Peters, Thomas Vesekny, Ike Schut, Matthias Sable, Terra Nova, Jonathan So, Walter von der Watering, Isabella Tomasic, Theo Winterhalter, Paul Wagner, Lucas Zielinski, Lionel Worth. Linux port by outoforder.cc, Linux testers Stefano Angeleri, Kevin Becker, John Drinkwater, Max E. Albury, with special thanks to Dr. Katrina Blomquist, Liam Blomquist, Space Captain Jordan Price, Ivy Gray, Christine M. Ho Esquire, Maslow, Capital 1360 Cafe, Tuesday Workday Friends, and Shalin Shodan and his guitar. Thanks to all these people for bringing this game to life. This is the end of my playthrough for Human Resource Machine. Thanks for watching. Bye.